We don't know how to do two completely different tests. There is a way of combining two tests. It's going to be a two sample. And we will learn how to do those in a few more weeks. So right now, all you can do is a one sample test where you put them together. And the reason that you're going to do a one sample test and put all this data together is because the data that is on line 1 all came from subject number 1. The data that's on line 2 all came from subject number 2. So the data is matched with itself. So whenever I think that these two numbers came out of the same subject or are a match of that subject, I want to, before I go any further, find the difference between those two numbers. Okay? So my alternative hypothesis needs to be that scented minus unscented is greater than 0. And now,
is this all part of step 1?
yeah. And now we want to check conditions and name our test. So we're doing a significance test for a population mean. What distribution are we going to use? Going to use normal or T? Are we given the population standard deviation? No. So we're stuck with the T distribution. And again, we have a single sample, but we'll call this a paired single sample. Okay. Next, we want to check conditions. I'm sorry, what? Doesn't matter. Which do first? Okay. Do we have a simple random sample of people working puzzles?
Well, do these people volunteer?
Subjects are volunteers. So we don't have a random sample of a population.
Is it an experiment?
It's an experiment. Did we talk about randomizing the experiment? Yeah, so we have a controlled randomized experiment. We randomize which order they did the scented and unscented.
Wait, so it's not a simple random?
No. It's a controlled randomized experiment.
Shouldn't you write SRS node then, and then write
So a controlled randomized experiment is as good as a simple random sample. So yeah, you could say no, we have a controlled randomized experiment, or you can just indicate we have a controlled randomized experiment rather than a SRS. That's fine. Is there a question? Okay. All right, normality. How do we usually check normality when we're doing the T distribution? Box plot. Box plot of what?
of the information
Of the differences. So we need to box plot the differences. So we're doing scented minus unscented, and that would be list 2 minus list 1.
So would you put that on like list 3?
Yes. So go into your list 3 and put list 2 minus list 1.
Oh, I never got any information.
Oh, yeah, you won't be able to do this. You'll have to just kind of go with us. Sorry. You could do a box plot for what you have. You're probably not very far off.
Is this example in the book too?
I accidentally cleared out my list.
Well, you'll be okay. There's actually no way to recover them when you clear them. There's no way to get them back out of memory. Yeah. Yeah.
List 2 minus list 1.
List 2 minus list 1. And so we'll make a box plot with list 3. It's kind of, do you see any outliers? All we're looking for are outliers. So my box plot doesn't look particularly skewed. It looks pretty, whoops, I've got that should be a box. It looks pretty symmetric. I mean, it's slightly skewed, yes, but not bad. Our sample size is bigger than 15. So we could go ahead. If you see an outlier with a very small sample size, then you probably want to say that we don't meet conditions.
Was there an outlier?
No, I don't see no. I don't see any outliers.
See none?
I don't see none. So we're okay to use the t-distribution. Even though it's a check for normality, it's really a check for approximate normality, and the t-distribution is approximately normal. Pretty darn close, especially with degrees of freedom as high as we're going to have. Okay. Last condition is about independence. So we want our subjects and their responses to be independent of each other. Independent, sorry. Subjects and responses need to be independent. So that means that when they're working on these puzzles, you don't want to put them right next to each other so they can copy. No, then we don't have independence in their results. It's probably okay to have them all be, of the same intelligence, or same or differing ages, since we have randomized here, and since each person serves as their own control. But we don't want to have any mixing of our data here. Yes, Judd? Independent. Okay. So so far so good. I think our conditions have actually been met for a change. Yes?
We're supposed to our sample size multiple of 10.
No, only if we're sampling from a population. We don't have a random sample. We're not sampling from a population. All right, our T statistic is our sample mean of list 3. What's our sample mean of list 3? Negative 0.96, can we call it? Okay. Minus our hypothesized mean, which is 0, divided by the sample standard deviation on list 3, which is 12.54, divided by the square root of our sample size, 21. We have 21 pairs of people. Our list 3 only had 21 values in it. Our sample size is 21. And yes?
My 0.96 is negative. Is that okay?
Yeah, you just subtracted the other way. That's fine.
Where is the 0?
Yes. The 0 is from the hypothesized mean.
Oh, yeah.
Okay. And what's our T statistic? Negative point, no, our T statistic. Negative 0.35. Negative 0.96 minus 0 divided by 12.54 divided by the square root of 21. Could be a parentheses problem, you're right. And to get my p-value, I need to do a t-CDF from, all right, which side are we looking at here? We're looking at a greater than. So we have to go from negative 0.35 to positive infinity.
When you say p equals, what's p?
That's called p-value. This is where we're going to make our, it's the probability we get a sample this extreme or